intuition. But that is a lie, right? That is a lie. How can you get the solution then? You have to do the separation of variable. Yeah? Takes a long time. And I will not ask you to do the separation of variable to get that solution. So can we agree that we use that solution as our solution then? Huh? Okay, everybody agree? Then I will go forward. Okay? You may think that, okay, the solution of trembling sphere would be somewhat similar with the dipole. Right? So we know the solution of breathing sphere is almost the same as the monopole solution, 1 over r e to the j k r. Right? Right? And the trembling sphere certainly push the fluid in this direction and suck the fluid in this direction, and then so on, so on. Okay? How to resemble that kind of wave field? If I put one monopole here and one monopole here with different phase, in other words, minus and plus, then what will happen? This will push the fluid in this direction and this direction, right? So that is dipole. So what is the solution of dipole? This is the solution of dipole, DDR. Right? Reason is I put the two monopole over here, and this is the distance delta r, right? And this is what I can get. Okay? So that makes sense. And the reason why I put cosine theta is physically justifiable. For example, the velocity potential, if I take a derivative with respect to theta, then when theta is equal to, when theta equals to 0, the velocity has to be maximum. Right? Right? When theta equals pi over 2, the velocity has to be 0. So the velocity potential must have a something that has to deal with cosine theta or sine theta. Right? It can be cosine theta or sine theta. Right? So, and then we can obtain pressure using this assumed solution, and that look like what? The pressure is look like more complicated from JK rho 0 C UC a to the cube cosine theta, and then 1 over 2 minus Ka square minus 2 JKA, and then I have something, and then e to the JK r minus a, and I also have a velocity that you can look at in the text. But the interesting thing is the radiation impedance is look like rho 0 C kr to the fourth, 4 plus kr to the fourth, and j 2kr plus kr to the cube, and 4 plus kr to the fourth. Okay? Okay. This one for breathing sphere, that look like kr to the square 1 plus kr to the square. But for the trembling sphere, the real part is a function of kr to the fourth instead of kr to the square. Okay, that means when kr is getting large and large, this trembling sphere approaches to rho 0 C radiation impedance more rapidly than breathing sphere. Okay? That we can say. So I can see that for kr equal 1, for breathing sphere, normalized the impedance was 1/2. But for the trembling sphere, when kr equal to 1, what is it? 1/5. So this should be somewhere over here. Okay? Okay? That means the slope over here is very rapid. So different characteristics. So we can argue that the trembling sphere approaches more rapidly to far field characteristics. But in a near field, the trembling sphere does not radiate as efficient as the monopole radiator in the near field. Okay, that's interesting. What about this one? The imaginary part, it looks more complicated. Okay. When kr equal to 1, that is 3/5. So this is 1/5, and 3/5 is somewhere over here. And then when kr go to infinity, kr to the fourth is much, much larger than kr or kr to the cube. So it approached to what? 0, but more rapidly or slowly? Rapidly or slowly? Slowly? Rapidly? We have to compare. So radiation characteristics of a trembling sphere is very different with what we observed for monopole breathing sphere. Then may I ask you, is it I understand this is middle of spring and the afternoon lecture is very nice to sleep, but important lecture, so please concentrate. Okay.